So welcome back, everybody, and to this new week of machine learning. Just a quick overview of the schedule for this week. So we are going to repeat a little bit about logistic regression, which is our first encounter with classification methods. And after that, and quite quickly, we are going to jump into, let me just do this one and increase the fonts a little bit. So we are going to run into stochastic gradient descent with examples. And one of the mathematical algorithms which we will spend some time on, both this week and also in the coming weeks, is something which is called automatic differentiation, which is simply an indispensable tool when we do machine learning. Now, you will find, in addition to these lecture notes, which you're viewing now, there's a good discussion on gradient methods by the textbook by Goodfellow et al., which brings you up somewhat more than mathematics. And then we have the textbook by Rashka, which contains discussions on logistic regressions and also some discussions on gradient descent, but more on the practical side. Now, when it comes to the lab sessions, this week is a kind of strange exercise. It's actually you trying to write an abstract, an introduction to the report. So in a way, this is a kind of attempt to have you started thinking about the report. And often it takes some time to write the introduction. So this is something which typically I really write at the end when I write a scientific paper. So the introduction and conclusion is something which I tend to spend a lot of time on after I've done calculations, methods, etc., etc. And we will also, during the lab sessions, we will discuss a little bit about how to structure the report, because roughly half of you have never written a scientific report before. And the way we're going to grade you is actually on the report. And that's the essential way by which we do the grading. And as you know, there is no final exam here. We just have 3 reports where each counts 1/3 of the final grade. So one thing which I wanted to do is actually to, before we do this, to jump a little bit back to what we did last week. So if we go back to last week, we started discussing logistic regression. And let me quickly bring up what we did last week, just as a repetition here. Now, one of the things we did then was to make an assumption about our data, where we now, instead of what we have done in linear regression, we assume now that instead of a continuous function, we have a probability distribution. And this probability distribution, instead of a function f of x, so this is a model which we have attempted to outline in order to describe f of x. Now we are going to replace this f of x with a probability distribution, and where we are going to use a so-called threshold value. So one of the most famous functions which you will encounter again and again is actually the so-called, so if we run down a little bit, you will encounter the first function, which is the so-called logistic function. And this is the one which we discussed at some length last week. And when you make a plot of that, you will see something like this. So let's just run this Jupyter notebook here. So this will be the sigmoid function. And you see now that this is a function which takes values which go from plus infinity to minus infinity. And at 0, the way we have set it up, it takes a value of 0.5. So one of the ways this function is being used is that when you have a value of less than 0.5, you would just output 0. When you have a value of above 0.5, you would output 1. So this is used as a function with a threshold to simply say that my output is going to be either 0s and 1s. Okay? So this is one of the most common functions, and we are going to meet it again and again. It's a function which also has analytical derivatives. So when we come, you can view this as a kind of first step towards neural networks, because we're going to use this function again and again in order to describe whether a neuron is sending a signal out or not. So if the value of this function is less than 0.5, we output 0. And if it's above, we output 1. So that's just a typical example of a function which you will encounter again and again, and which also allows us to define a probability, as you could see from the equations here. So this is the function, and you can then say that the probability of 1 is equal to this function, and the probability of 0 is 1 minus p of t. Now, other functions which you will encounter are functions like the step function. This is another example which we could use. So this is a step function which is then centered around 0. Now, one of the problems with the step function is its derivative. So coming back to what I mentioned about automatic differentiation, which in a way is what saves the day when we are training a neural network, this function here is less friendly in the sense that the derivative is going to have a discontinuity. And that's one reason why it's less used in the literature and in applications. Another function which you will meet many, many times, which has similar properties like the sigmoid, is the tanh function. And in neural network and deep learning calculations, people often play around with different so-called activation functions, as we described last time. So let me just take away that one. And what we did was simply to look at a case with 2 parameters last week, where the function which outputs 1 was then given by this function here, which had the parameters beta 0 and beta 1. And then we had the case with the y of I equal to 0. So that's one of the outputs. And a data case which we are going to look at pretty soon is this famous Wisconsin breast cancer data case, where you simply output 1 for, I think that's a malignant tumor, and 0 for a benign tumor. And the function which we end up to train is given by these parameters beta 0 and beta 1. And then we use the maximum likelihood, where we now set up a function where we take the products of all the probabilities, either for p of I equal 1 or p of I equal to 0, and which is this case which you have here. And then we train the log of that function. And when we train the log of the function, we're actually taking the derivative of this function, or we can take the negative of that function. So we can either take a maximization approach or a minimization approach. And you can also add these regularization terms of type L1 and L2, as we have been doing in linear regression. And that adds more parameters. So when we are minimizing this function, the thing we went through last week was a calculation of the gradients with respect to beta 0 and beta 1. And the thing now is that we don't have analytical expressions, simple analytical expressions for the parameters beta. And we actually have to solve these equations numerically. And the standard approach for solving them numerically is Newton's method. That would be the plain, straightforward way of doing that. And I will remind you quickly of that, because that brings us in to gradient descent methods immediately. Now, what we had then is a more compact expression, and then we also have the second derivative here. And this is typically the function which we end up dealing with, this gradient here, for logistic regression. If we have other types of probabilities we are trying to fit, we will have to look at different functions. The second derivative now involves a matrix W, which has non-diagonal elements 0, but then along the diagonal, it contains the unknown parameters beta. And this is something which makes life a little bit more difficult, because in linear regression, we did not have the W, and there was no dependence on beta on the parameters in the design matrix X. This is something which makes the implementation of Newton's method much simpler. Now, one thing you can do is to have more features or predictors, as they're often called, or properties. So that means that you can have, you could have now X1, which could represent the size of this tumor. X2 could be the color, etc. And these will be features which then are used by, let's say, a pathologist to classify whether this is a bad tumor or not. And then you would have more parameters to fit, which means obviously that your design matrix becomes bigger, right? If you have only 2 parameters and let's say 100 input values, then your matrix is just 100 times 2, as we've seen in linear regression. Except that now the outputs are discrete values. So instead of having a continuous function, even though if we have a continuous function, we always discretize, because we cannot deal with an infinity of variables in our computers, sadly. It's a finite box with a finite memory of which you can store, which you can use to store numbers. So you can also include more classes, and we are coming back to this when we start looking at implementations of neural networks. But just keep this in mind that you can, there is a simple way by which you would typically implement more classes, and this is called the softmax function, which we are coming back to a little bit later. And in the material here from last week, this is just a quick reminder from the lab session last week. You can find examples on how you can find for project 1 these optimal parameters lambda. So you have a grid search and you have a randomized search, which are functionalities you will find in scikit-learn. So feel free to use this in the project. So I'm not going to comment this because these are things which we discussed in the lab last week. So there's a grid search, there's a randomized grid search. Feel free to use these. Now, the test data we are going to look at is now the Wisconsin breast cancer data. And I just wanted to say something about this specific example, because there are some other things you can do with scikit-learn, which gives you quickly some insight about the data. So when you apply an algorithm, it's very easy to just forget about thinking about the data. Because sometimes we can visualize the data in ways which give us a lot of information from the very beginning. And let me just quickly show you that. So one way which we are going to look logistic regression. And let me just do one small thing here for those of you. I just need to, yeah, now you should hear me better. So in this specific case, we are training and splitting the data. There is a data set in scikit-learn, which is just this cancer data. So we don't need to do anything here. So it's already there as a data set available in scikit-learn. And you can see now that when I train logistic regression here without doing anything, this gives me now a precision of 94%. So what this is counting is the number of cases I've classified correctly. So you simply run over all the ones and zeros, yes and no's, and see how many of these you classify correctly. And I use roughly 80% of the data for training and 20% for testing, as before. And then you see now that I get a 94%, which is not so bad. You would like to do better. And you will see later that we have methods which will give us a hit of close to 100%. So this first attempt with logistic regression is perhaps a result which you may not be too happy with, especially if you know that you can use methods like boosting methods, we will come back to later, which can give you a training accuracy on test data, which is close to 100%. Now, one thing which is useful to look at is a way to split the data. And there is a way where you can take this data and set up bins of histograms where you count the number of benign and malignant cases. And you can also plot the correlation matrix. So you can now see, if you look at this case here with the mean radius, this is a case where the bad ones and the good ones are almost nicely separated. So by looking at these data sets, you could say now, okay, if the size is smaller than 15, and I think this is 15 millimeter, I don't remember exactly, but I think it's 15 millimeter, then you can say that, okay, in most of the cases, this is a good case. So by making such plots of the data, you can quickly get a kind of overview of what kind of data are easy to understand and which one are perhaps a little bit more complex. Now, what these data mean for pathologists, since I'm not a pathologist, is something which I cannot explain properly for all of the data, but some of them are pretty intuitive, right? Like the mean area. I don't know what these things mean, not all of them. Radius error, perimeter error, etc. So some of the cases are cases where you have basically no overlap, and in other cases you have actually cases with a strong overlap. One thing you can look at is also the so-called correlation matrix. So here, if you remember back to what we defined in the beginning of the semester, we discussed this covariance matrix. So if we divide the covariance matrix, all the entries, by the variances, then on the diagonals, we should have either minus from -1 to +1. So if you have something which is 1, and you look at that together with another feature, so if you look at some of these columns here, and you look at the mean radius here, and then you look at the mean area, you will see that this has a correlation of basically 1, which in a way is expected. This means that when you look at your design matrix, and if you think back in terms of linear regression, it means that you would have features in the design matrix which would be almost equal by just a constant. And that would give you problems with matrix inversion, obviously. This is a kind of pre-data analysis, which is extremely useful to look at, because it gives you a kind of feeling of which data could be the important ones and which data could be less important for a classification problem. Okay? Now, during the lab sessions, we are going to look at some of these other properties on how we discuss this correlation data. So this is something which I will leave for a little bit later. And we have some measures which you will encounter during the lab sessions. And one of these is called the confusion matrix. But we are going to discuss that a little bit more in detail later. So the confusion matrix for a binary case is very simple. So it's true positive, so you classify correctly. And then you have false positive. So if you look at this case here, you have 96 of the cases which are true positive, which are classified correctly. And then you have the false positive, where you have roughly 4% of the cases. And then if you scroll down, so this is a very easy way to display how well your model is doing. So this would be false negative, and then this is true negative. So either 0 and 1s, and how you classify these types of tumors correctly. So this is another way to visualize the data. So when we are coming to project number 2, and the reports we are going to write in connection with project 2 or 3, if you do a classification problem, this is a typical way you would display the quality of your model by a confusion. And this is pretty intuitive when you look at it, right? And we are coming back to this. Now, what I want to do now is to go back a little bit to the lectures this week. And we are going to, after we have revisited the equations here, so these are the equations we are going to look at. I wanted to bring up what we did last week in connection with Newton's method. So let's slow down the pace a little bit and switch to the whiteboard. So what we did last week was now to make a Taylor expansion around the optimal value of beta. So let's quickly remind ourselves about some of the quantities we want. So in Newton's method, which is the starting point for essentially all these gradient descent methods, what we did was to make a Taylor expansion around the optimal parameter beta.
Cost function around a value which came from a previous iteration. So this beta n stands for an iteration which we have been doing. And after a given number of iterations, we have reached the optimal value. So what we're assuming now is that we have a value beta n, which is pretty close to the one we want to have. And then we made a Taylor expansion. So let's quickly remind ourselves about that. So we Taylor expanded.
And this was a Taylor expansion around the optimal value, this beta hat. So that means that we have a cost function C of beta. And this is obviously given by C of beta of n, which is the value we are starting with. And then we got, when we wrote this in terms of matrices and vectors, so we would then have a vector beta. So these are now, if we have two elements, then this is a vector of length 2. So this is transposed, and then we had the gradient. So this is a derivative of the cost function, evaluated at beta of n. And then we had a second order term, the second derivative term, where we have a beta minus a beta of n transposed. And then we have this Hessian matrix, which is the second derivative. And this is then multiplied with beta. And then we have this beta of n. And this goes on with higher order terms in terms of these parameters beta. So this will be this difference to the power of 3, etc. Now, what we did then, and let me quickly remind you of what these expressions look like so that you have them back again. Now, what we did then was simply to truncate this Taylor expansion at the order of the second derivative. Now, for those of you who have studied optimization problems, this is essentially the starting point. So is anyone who here who's done the mathematics of optimization problems? Okay, some of you have looked at that. Essentially what we do is to stop at the second derivative. And that means that what we have then is a function C of beta, which is approximated at the order of the second derivative. And now I'm going to repeat what these terms are. So I'm going to have a beta minus beta of n transpose, and this is the gradient, C of beta of n plus 1/2, and then we have a beta minus beta of n transpose times this Hessian matrix evaluated at beta of n multiplied with beta minus beta of n. And what these terms are, if we now think of linear regression, so this is something we could have used for linear regression as well. So in linear regression, we know that this gradient of beta of n, that is nothing but the cost function for, let's say, the mean squared error, evaluated at beta equal to beta of n. Then for linear regression, we had a special relation for this matrix n, and that was given by 2 divided by n, and then we had the design matrix transposed times x. Now, one important aspect here is that this is independent, and we are going to use that feature a little bit later. This is independent of the unknown parameter beta. Okay. Then, if we look at logistic regression, we have another expression for these derivatives, for the gradient. And we have another expression for the Hessian matrix. So this quantity which we have here is something which we call the Hessian matrix. And that is essentially the second derivative of the function we want to optimize. So if we then went to logistic regression, and now I'm setting up the second derivative. So this dc of d of d beta hat, this is equal to this design matrix, which is independent of the parameter beta. But then we had this quantity here, which is now a probability, which depends on beta of n, multiplied with this probability, and I'm putting indices I here. So this is the diagonal matrix element. So I stands for an input x of I and an output y of I. And then this is evaluated at beta of n again. And you see now that you have an explicit dependence on the parameter beta. So this is 0 if I is different from j. So the non-diagonal elements are non-zero. This is a case for logistic regression in the simple form with the sigmoid function for the probability. If you were to use another function, this expression would be different. Now, what we ended up with then is an algorithm. When we collected all these things, we could then find an algorithm for beta, which is now equal to beta of n plus n. So we call this for n plus 1. So this is iteration n plus 1. So we have a previous value. So we start with a guess, and this is minus h of beta of n inverse multiplied with a gradient evaluated at this value beta of n. So that is Newton's algorithm or Newton's method. Actually, it's called Newton-Raphson. So this is a starting point. So if we can calculate this Hessian matrix, then we're pretty happy, because then we could try to perform these iterative steps and then move on, and hopefully this would converge. Now, we are going to look at many delicacies here, because everything which we are going to do will depend on the starting point, where we start as an initial guess, because we could start in a wrong place. So when we are performing this kind of calculations, suppose now the function we want to optimize as a function of beta. So we have a function here of beta, and if we suppose this looks like something like this, if I start here with a beta 0, then I calculate the gradient, which hopefully brings me down to here, and then gradually down to this point. But that would not be the global minimum which we are looking after. We would then be stuck in a local minimum. So when we deal with machine learning, we are trying to find ways to avoid being stuck in a local minimum. And when we are going to introduce neural networks, you're going to have so many parameters that's actually often difficult to gain a kind of intuition about where is the minimum. So when we are dealing with logistic regression and linear regression, these are functions which are normally convex functions, like we saw for standard logistic regression. And then it's pretty easy to actually find the minima with the right starting point, obviously. So clearly, the guess here is also something which is going to be important for us. So one thing we did last week, let me just bring that back. We also made an iteration in order to find a parameter beta. So what we did then was to replace the Hessian matrix. So we have this beta of n minus this parameter gamma, which we are going to call for the learning rate. So this is called the learning rate. And last week, we found then that when we took the derivative with respect to this parameter gamma, we could find a mathematical expression for that quantity. So I'm just going to repeat that. We did again a Taylor expansion, where we now made a Taylor expansion around. You'll be surprised to see how important the Taylor expansions are. Taylor expands C of beta around beta of n minus gamma of n multiplied with this g of n, which is now the gradient at beta of n. So last week when we did that, then we found an analytical expression for this parameter gamma. Now, then this parameter gamma, what we found when we took the derivative of that function with respect to that one, is that we could write this as a function of the gradient transposed. So keep in mind now that this is the gradient evaluated all the time at a value of n. And this was divided by G multiplied with a Hessian matrix, which is also evaluated at beta of n times G. Now, this method has a name in the literature, and this is called steepest descent. And it's a very popular method if you can calculate the matrix H and the dimensionalities are not too big. It's going to be slow because it's going to just take every gradient in each direction. There are mathematical methods which are faster and better, which are the methods you would use here. And these are called the conjugate gradient methods. So there's a whole family of methods which are used to cases which look like that, where you can calculate H. Now, the problem which we have when we look at a neural network is that H may be a matrix of dimensionality 1 million times a million. And that means that you have 1 million beta values. And if you're going to do that iteration 1,000 times, you will need to do this 1 million times 1,000. And the matrix H and the gradient change for each value of beta. So that means that a method like the steepest descent, which has a simple mathematical formula, and is a very popular method in linear algebra and optimization problems, is a method which is less usable for us when we go to multidimensional functions which we want to evaluate. So I hope you see the philosophy here for why we are now going to introduce a much simpler approach. So the standard starting point, which we will deal with, oops, not there. I lost my notes here. Here we are. So the starting point is the gradient descent method for finding the optimal parameter or parameters. And that means that we have an iterative process with beta of n plus 1, which is equal to beta of n plus or minus, normally, a parameter, gamma of n, where gamma can just be a fixed constant, multiplied with a gradient evaluated at beta of n. Now, one thing you will see quickly is that even the calculation of the gradient is numerically time-consuming. So if you have a set of parameters which is pretty large, even the calculation of the gradient can take a lot of CPU cycles. And that leads us to ways to try to make this even more efficient. And that parameter gamma, which you see, this is one of the parameters which we're going to fine-tune. So this parameter here is normally called the learning rate. And we are going to look at different ways by which we can find information about this learning rate, which reflects the problem itself, which often means bringing in information from the gradients. So there are several approaches which we are going to look at now. So one, so different approaches. So you can see that one of the bottlenecks in all of machine learnings is actually this optimization problem with this parameter gamma. So one is obviously keep gamma fixed, gamma of n equal to a parameter gamma fixed for every iteration. That's the simplest possible approach. And then you would choose a set of parameters. Choose gamma, could be something like 10 to the minus 5, 10 to the minus 4, and this could go up to 10 to the minus 1, just as an example. So that's one possibility. Now, the next approach, which improves considerably upon the standard plane gradient descent, is gradient descent with momentum, which we're also going to discuss. And I'm going to use the shorthand GD with momentum. I actually prefer to call it memory. I think the name memory is better, but this is inspired by a rewrite of Newton's equation, where we have a friction term or a drag term, which is then related to the velocity. And the reason for this naming momentum has to do exactly with that. But in other cases, this kind of way of dealing with the iterative process reminds you of you keeping information about previous values. So in some other cases, this is just called a memory term or memory method. Then we have methods like ADA-grad. This is adaptive gradient. So in that case, this gamma has info about the gradient. So ADA-grad is a very popular method. And what you will often see in the literature is that people tend to play around with different such methods. And then they pick the one at the end, which gives the best result. So we're also going to encounter another method, which is called root mean square propagation, or RMS prop. And this is also a method where gamma has some information about from the gradient. And finally, we have the method which I mentioned last time, which is adaptive gradient with momentum, and that's just called ADAM. That keeps also some info from the gradients. And what you will typically see in essentially all machine learning implementations is that people play around with all these methods or subsets of these methods, and then you would pick the ones which give you the best results. Now, ADAM is a method I mentioned which has, since 2014, now close to 200,000 citations. So this tells you how big an impact you can make if you can speed up the process which you see in the previous equation, which is this equation here. So this equation is one of the basic equations behind the optimization part. And the reason for why we do that, instead of widely popular methods like steepest descent or conjugate gradient descent, or conjugate gradient as they're called, and variants thereof, is simply because these other methods, which are better from an optimization point of view, require that you calculate the Hessian matrix. So keep in mind that the Hessian matrix, if you now look at the case like we have here, or in linear regression, where the Hessian matrix does not depend on the parameters beta, are cases where this is simpler to evaluate. And often this matrix, the Hessian matrix, is not very large. So for the Wisconsin breast cancer data, the matrix has 30 features, so it's a 30 by 30 matrix. And we can still do it. So it's something which you could implement in a more brute force way and see if these other methods work better. But now we are going to look at some codes and try to gain some kind of intuition about these different methods. So let's go back a little bit to, I just wanted to mention one result, which we also discussed last week. And this is a result I'm only stating, and that is that the optimal value, and you can actually show that if you have a convex optimization problem. So the optimum value is a gamma, which is smaller than 2 divided by the maximum eigenvalue of the Hessian matrix. So this is the eigenvalue of H. And when we do logistic regression, this is actually the Hessian matrix evaluated at a given value beta of n. So any questions? Does it sound clear what's the task we have to deal with? Okay, so what we are going to do now is actually to go into some of the codes and just take a look and get some feeling for what is coming. By the way, I just wanted to give you a simple example before we take a small break. So one example of a function we want to optimize, and where you could actually do this by hand and follow the steps. So you could take a function now, which is given by f as a function of 2 variables, x1 and x2. And we can write this in terms of this kind of expression which we had earlier. So we have x1, x2, and then we have a simple matrix of 2, 1, 1, and 20. And this is then multiplied again with the vector x1, x2, minus, and then I have a new vector, not transpose, but multiplied with x1 and x2. So this is close to the expression which we looked at. So we have an x transpose times a matrix A minus a vector B times a vector X. So if you look back to what we did with the Taylor expansion, so one term would simply be this one. That's the term with a vector B transpose times another vector. And the other term is actually this vector times a matrix. So if you look at this example again, what you have here is essentially the matrix A multiplied with a vector X, and then we want to optimize with respect to that vector. So if you write it out, this is nothing but a function which goes like x1 squared plus x1, x2 plus 10, x2 squared minus 5, x1 minus 3, x2. So this is just another way of writing the type of problem through a simple example. And now you know when you optimize this and you want to find the optimal x1 and x2, you take the derivative with respect to x1 and x2. So what you would do then is to take a derivative. So these are the gradients, x1, x2 with respect to dx1. And that gives you simply 2x1 plus x2 minus 5 equal to 0. And then you do a d of f of x1, x2, and d of x2. And you want that one to be 0. And that's simply x1 plus 20, x2 minus 3. And these are equations which we can solve, right? So what we would find then is that x1, in this specific case, is 97 divided by 39, which is approximately 2.47. And then I have that x2 is equal to 1 divided by 39, which is approximately 0.026. Now, what I could do next is simply to define an x0, which is my first iteration, which I put to minus 3 and 1. And then I would use the formula from Newton's method, which simply says that this is x of I minus this learning rate multiplied with a gradient of d of f evaluated at these values x or y. And this is now a vector. So you could then start with a guess of x0. You would insert that one, and then you would keep iterating till the difference between the left-hand side and the right-hand side is just less than a number which you have chosen. So if you want to gain some intuition about everything we've been doing now, this simple example actually contains essentially everything which we are going to do, except that in our case, these vectors are going to be multidimensional ones. So instead of having just two parameters, x1 or beta0, beta1, as we've been calling them, we would now simply have many more parameters. So one thing I would like you to do now during the break is simply to take down the Jupyter notebook for this week. And we are going to look at some runs. So before we take a small break, so if we scroll down a little bit, here are some basic mathematics about ordinary gradient descents. And there is also a discussion of these different methods, which we have just mentioned. And then we are just going to revisit this problem, which we had in the first homework. And we are going to, instead of inverting the matrix, we are now going to implement the gradient descent method. And then we're going to play around a little bit with learning rates and these parameters and see what we get. And then we are going to move over to momentum, gradient descent with momentum. And later on, we will move on to ADA-grad and these other methods which are used to tune this learning rate. So we are now opening up this huge box of tons of parameters to fine-tune. And this is where many of you feel a kind of disappointment that now we are just tuning tons and tons of parameters over and over again. But this is what we have to live with when we're dealing with machine learning methods. Should we take a small break? Just stretch legs 15 minutes and you can just, I mean, this place is pretty enjoyable actually. It looks pretty nice. Yeah. Okay, let's take a small break and feel free to ask questions. So when we are iterating with these gradient methods, sometimes when you run software from scikit-learn, you will get a message of the type too few iterations for the precision you have chosen. And this normally means that all these methods with a gradient descent, like lasso, which also uses gradient descent, logistic regression, etc., they rely on a certain number of iterations and a precision which is preset. So you can change these parameters, but you have to go into the appropriate libraries and try to find where you set the parameters, such as number of iterations and the precision. But this is a typical test which we end up implementing when we are running these methods. Now, in the codes which we're going to look at now, I haven't put this test. So I'm just running this as a function of number of iterations. So let's go back to the codes and take a look at some simpler examples, which hopefully can give us some kind of insight about these gradient methods before we then move on to more advanced ways of updating this learning rate. So the example which we are going to look at is one which you have seen many times. And what we have is just a simple data set with some random numbers with a uniform distribution between 0 and 1. We have 100 data points, and we have a simple straight line as function, which we want to fit. And you can play around with and without the noise here. So if we now look at the function we want to fit, we are making a fit of a linear function. And it means that our design matrix, So this is just a reminder of what we have seen many, many times. So the design matrix is now given just by once, and we keep the intercept, and then we have 100 data points. That means that the cost function which we have with just two parameters, the mean squared error, the simplest possible case, is now just given by these parameters beta 0 and beta 1, just plugged in here. So that's nothing but what we have done before. And when we calculate the derivative, we see now that we can write this out in terms of two terms, one for beta 0, so this is a derivative with respect to beta 0, and this is the one for beta 1, which we then can also write in a more compact way like this. Now, pay attention to one thing, which is also an important aspect in all these methods. Now, here we have only 100 data points, which is a pretty small case. But in general, we can have thousands and thousands of data points. So that means that the evaluation of the gradient is in itself something which can become expensive for the parameters beta, which we have here, and the amount of data points, okay? So we are, even such a thing like a gradient does not need to be a trivial thing to calculate. So here it's pretty simple. And we can then set up also the Hessian matrix. So in this case, it's just a 2x2 matrix. And in the examples which you see here, you can actually play around with these different Hessian matrices and see if that gives a decent result or not, if we use the eigenvalues of the Hessian matrix. So this is a convex function, and it has only positive eigenvalues. And the program you see here does this in an iterative way. We start with a guess, which often is just a random value. And then you start iterating. And where you have the gradient of the cost function, you could stop iterating when this gradient is smaller than a given quantity. So the code below does not have such a stopping criterion. So this is obviously something you would implement, and you're actually going to write your own gradient descent code in project number 2, because you will need this when you're implementing the code for a neural network. So these basic steps are steps which you will see now again and again here. So the example which we have is us now setting up the data. So you can leave out noise if you want to, or just keep it. So let's now just leave it out. And you can see the Hessian matrix which I'm setting up. So what I'm doing here is first to use what you have done till now, just a linear lin-alg inverse. So we're just calculating the beta parameters by doing what we've been doing in project 1. And then I'm setting up my own iterative scheme. And you can see how simple this can actually be done when you set up the gradients. Now, here I choose the parameters beta for the iteration to be random numbers using a normal distribution. I have only 2 parameters, so everything is preset. What I do now is to choose my eta to be equal to 1 over the max eigenvalues of the Hessian matrix. So here I calculate, so I'm actually being guided by this formula, which tells me what value eta should have when I start iterating. Now, keep in mind now that in this case, so let me bring that back. This design matrix does not depend on the unknown parameters beta. So this is a kind of gentle case, because what I can do now is simply to invert the matrix once and for all. And I can diagonalize it once and for all. There is no beta dependence. If I do logistic regression, I will actually have to recalculate it for every value of beta, because the Hessian matrix will depend on the parameters beta, the unknown parameters. So linear regression is one of these gentle cases, which saves us a lot of painful thinking and painful work, programming work. So in this case, I then use this, instead of 2 here, which is a limit, I just put 1. And now I do this in a pretty brute force way. So what you can see here is in the simplicity of what we are doing. There's no breaking criterion for the parameters beta. So I could have actually, what I could have done here is actually to calculate the difference between beta and the previous value, beta new. I could call this a beta new minus beta old. And then if that difference, if diff less than, I'm just writing it in now, some epsilon, then stop. So let's just take that away. This was just a quick way of inserting that element of code. And what I'm doing now is simply to run this code. And you will see now that the eigenvalues of the Hessian matrix are positive, as they should. This is a convex function. This is what matrix inversion gives me, the standard recipe you have been using again and again. And this is what my method gives me. Now, what I could do now is clearly to change this eta value. And I could put it to 0.99 instead, just a large value, and see what happens. So I get a none. Now, one of the things I would like to do now is actually that you guys just take this code, which we have, just the notes, that specific example, and then we simply go in here. Well, let me just do that. Something went wrong. Click to reload page. Here we go. So try to run this code and change just the learning rate. And when you're done, then you can just set up your responses. So we just take some 5 minutes and simply run that code and play around with different learning rates without changing the number of iterations. And then we need to think a little bit about what can go wrong. Okay, so let's take some 5 minutes and just play around a little bit. And if you want to punch in your response, you can do that. Or we can just discuss that together in when we summarize things. And feel free to ask questions while we are making this kind of analysis here. So the code is pretty fast to run. So if you have some responses and you would like to punch them in, I mean, feel free to do that. Is it okay if we take 2 more minutes? Is that okay with everybody? And then if you want to, you can feed in your responses. Yeah. Excellent. Yeah. Cool. Yeah. So if we just take 1 minute more, and then going to see if we have more responses. Okay, any more responses? If we now look at what we have here, there are 2 responses. So next time we'll hopefully have a little bit more responses. So there's one response which says you get very large values for beta. So what kind of learning rate would you then expect? Would that be a small value or a large value for the learning rate? Yeah, a very large value. And then you're saying that greater learning rate means that the betas, yeah, too few iterations is also something. You can actually increase the number of iterations. If you make this small, if you have a small learning rate, you would need more iterations to get a better result. So there is a simple graph you can make. And this graph says essentially everything. And if you keep this kind of picture in mind, that is the kind of things we will see in a more general case when we have more than just these 2 simple parameters. So let's just take a quick look at the whiteboard notes again and try to see if we can gain some deeper intuition about what is going on here. So if we look at the approach which we're dealing with, suppose now that we have a function which looks like this along the beta axis, and then we have a function c which we want to optimize, and that this function is a pretty simple convex function which we are trying to optimize. And we want this specific value here, which is going to be our beta hat, and the result we want to achieve after n+1 iterations. we would typically start with a given value of beta 0. This is our first guess. And then depending on the size of the gradient, we will move to the next point, this one. And then we will hopefully move at a certain pace down to this minimum. So after a given number of iterations, we would then be down here, like that. Now, this would be a learning rate, or this parameter gamma, which gives us a result which is desired. So this could be a gamma which is close to optimal. We don't know exactly whether it is close to optimal or not, but this would be a gamma value which now drives this term of G. G is the gradient, where we could say that gamma, we have an optimal value. Then some of you saw that when the values of beta, the optimal, just diverged totally, we even got not a number. In that specific case, we could get something which looks like this. We go to this point, we go out here, and then we go far away. So this would be a learning rate, which is larger than 2 divided by this lambda max, where lambda is the eigenvalue of the Hessian matrix. So this would be a case which would diverge, and then you saw that you got these crazy results, right? Now, what you also saw is that if you made gamma very, very small, so that means that we make very, very small steps. So suppose we are moving here in very, very small steps, and then it stops here. And this is an example of too few iterations. So gamma, too small. Now, one thing which can also happen is that the gradient is very small. So even if we have an acceptable gamma, the gradient may be so small that we barely move. And that's another problem which we will encounter. And in the machine learning literature, there's something which is called vanishing gradients. And that's a situation which almost killed the field of neural networks, because functions like the sigmoid function we met before the break takes values which are pretty close to 1 or 0 when the argument goes to minus or plus infinity. And then the function is flat, dead flat. And with a function which is flat, and you take the gradient of it, you have a gradient which is vanishing or exactly equal to 0. So that's another problem which you will face in this kind of trainings. And this kind of figure represents, in a certain sense, all the nightmare which we face when we deal with machine learning methods. So if you can keep this kind of image at an overarching level, this is the kind of basic message when we now are going to move on and try to tune these different parameters. Now, in the lecture notes, you will find many examples. You will also find one for ridge regression. And I just invite you to take a look at it. Now, what we are going to look at now is a method which is called momentum. So gradient descent with momentum, which in principle will allow us to get a better speed up with less iterations. So let's try to get an understanding of what that improvement of plane gradient descent means. And it's actually a very small change you need to make to the codes which you saw previously. So let's look at the first modification of the gradient descent. So what you saw in this example is us implementing gradient descent for linear regression. So the only thing you need to change is actually the derivatives and the cost function you want to look at. This is something which so in the lecture slides this week, there's actually more information than we will cover this week, because there's some information which we will also continue with next week, and that deals with automatic differentiation. So these codes which you saw now, which are in a way handmade for the specific case, are codes which we will change so that we can automatize it. So you can just give a cost function you want to calculate the derivative of. And then with automatic differentiation, that will calculate the derivative to numerical precision. So here, we actually plugged in the analytical expression for the gradient, which we know it's easy to find. But when you deal with neural networks, you often want to change parameters quickly, and you don't want to go through the hassle of hard coding derivatives. So sometimes that can speed up your code. In most cases, it does. But you have to, when you think of coding, what you also have to think of is to try to strike a balance between your time and the number of CPU cycles which the code is going to take. So if it takes you half a year to encode derivatives in the code, and the only gain you get by that is something like half the CPU time, and you're running the code for, let's say, 1 month, it's clear this half a year you spent on getting the analytical derivatives. If you replace that with automatic differentiation, then your total time is going to be much smaller. So there's always, when we think of hard tuning a code, one thing is runtime, but the other thing is your development time. So in my field, where I've been using these methods, we often spent months to get analytical expression for gradients till the automatic differentiation project becomes so efficient that we could actually just plug in new functions and let the computer calculate the derivatives. And that saved us a lot of development time. So this is also some kind of balance we need to strike when we are developing numerical software for machine learning. But we are coming back to automatic differentiation. So let's now look at this new method which I mentioned, which is gradient descent, GD, with momentum. And see if we can gain some intuition on why this is actually better than plain gradient descent. Okay? So the inspiration here is actually Newton's method or Newton's equation. So if you think of a particle which moves under the influence of a force, so we have a particle moving with some friction or drag, and with force. So this is moving with an external force, which is now with force f of x, which is now given by the gradient minus the gradient of v of a potential v of x. So if you think of the gravitational force, which is one of the classical examples, then you have a gravitational potential and you take the gradient of that one, and then you have the force acting on the object. But let's keep this at a very general level. And Newton's equation then of motion, the famous one, this equation of motion is then simply given by some mass term. We have the acceleration. We have a second derivative of the position. We have some friction term or drag term, if you're looking at air resistance. And then this is equal to this delta V of x. So this is something you can think of as our gradient. Think of as our gradient. This is normally called a friction term, and it's proportional with the velocity. So this term here, mu times the velocity, acts like a kind of momentum. For those of you who are physics aficionados, I mean, if you have studied Newton's method, this is a typical variant of it when you add friction or some resistance or whatever. Okay? Now, the thing which comes next is the way we are going to approximate this numerically. And there is a famous formula. So we're going to discretize derivatives. The first and second derivatives. And the standard formula, which many of you may have encountered. If you have not, this is again something which, to some people's disappointment, is just a manipulation of Taylor expansions. So many of the famous formula for derivatives are actually based on simple manipulations of Taylor expansions. So if you Taylor expand around an x of t plus a step delta t, so delta t is a small step you make, and then you Taylor expand around x plus delta t and x of t minus delta t, and you sum or subtract the two terms, you get an expression for the second derivative. So this is an approximation. And then you do the same thing with the first derivative, which is simply given by Euler's formula, divided by delta t. This is Euler's famous formula. So you have chosen a time step here. Now, later we are going to change this way of thinking in terms of iterations. So this t plus delta t is going to be an iteration n plus 1. T minus delta t is going to be iteration n minus 1. Now, so these are famous equations which are used in many differential equation solvers. Now, I'm also mentioning this because this gives you an approximation to the derivatives. This is not the formula you use in automatic differentiation, because this will give you wrong results for higher derivatives. You can take that formula and use that to calculate higher derivatives of e to the x, and you will get wrong results. So automatic differentiation is something different. It doesn't use this finite difference formula, which are very popular in many numerical algorithms. That was a small digression. Now, what we do now is to define two new quantities, and then we can rewrite the equation. So I'm going to define a delta x of t plus delta t as the difference between x of t plus delta t minus x of t. So I'm going to take one of these xt's here and rewrite that one. And then I'm going to have a delta x of t, which is actually x of t plus x of t minus x of t minus delta t. Then I can rewrite the equations in terms of this delta x plus delta t. So I'm simply going to now multiply out this term here. I'm going to plug this in, these terms and these terms. I'm going to plug them in back into the equations here, in this equation and that equation. And when I've done that, I'm going to multiply out delta t squared. So that means that when I reorder, I'm going to get the following equation. So I'm plugging in these approximations into Newton's equation. And this is going to be given by minus delta t squared divided by m plus this parameter mu times delta t. And this is multiplied with the gradient of v of x plus a term m divided by m plus mu times delta t multiplied with this delta x of t. So what I'm going to do next is simply to introduce two new parameters. So I'm going to call this term here for a parameter gamma. So I'm going to call this one for value gamma. And then I'm going to call this term, which you see here, this one, or without the minus sign, this I'm going to call for a parameter. Sorry, no, I've mixed up here, right? So this is what I will call for a gamma. And this parameter here is something, or these terms is I'm going to relabel as a delta. Now, one thing you can see now, if you look at this parameter delta, if I look at this lim delta, no, lim of delta when mu goes to 0, then it's easy to see that this is actually going to approach 1. And if I take lim of delta when mu goes to infinity, then this one is going to be equal to 0. So I'm assuming that m and mu and delta t are larger than 0. So this means now that this delta takes values between 0 and 1. Okay. So with that, I'm going to rewrite the equations as a delta x of t plus delta t is equal to some parameter gamma multiplied with the gradient which we have, v of x, plus some delta, which is a parameter of x of t. Now, if I now change my notation, so I let this x of t be my parameter beta for iteration I. So let me just rewrite that one slightly. I'm going to rewrite it like this. So there's an iteration I. I'm going to let this x of t plus delta t be replaced by my beta at the iteration I plus 1. And then clearly this x of t minus delta t is going to be replaced by a beta of I minus 1. And I'm going to let the gradient delta v, which I have, that's going to be replaced by g of beta of I. Then I can rewrite that equation as a beta of I plus 1. So this is my iteration here, equal to a beta of I minus, and now I have this parameter gamma multiplied with a g of beta of I, my gradient, plus a term delta, where I now have some kind of memory about my previous value of beta. So you will often see this delta being called a memory term. Now, why do we do this? Now, one reason for why we do this is that sometimes the gradients can vary a lot. So when the gradients vary a lot in the search for the minimum, then we are going to jump from extreme values to extreme values. So the hope here is that we actually, by keeping this information from a previous step, that we actually end up with taking a kind of average over different values of beta, and that smears out larger fluctuations in the values of beta. That's the kind of hope here. Now, this beta becomes this delta becomes a parameter again. So, which we can fine tune. So in this kind of parameter is something which people in many other fields have introduced in a kind of ad hoc way in order to have information from previous iterations. And hopefully that can dampen large variations in the parameters, beta. So this delta is something which we then will tune, obviously. So if we now look at the small rewrite of the algorithm, so the algorithm here, which we would implement, compared with standard and ordinary gradient descent, runs now as follows. So we would fix obviously the initial values, initial guess for beta, which in our case will be beta 0. And then we would also need to set this parameter delta, which we have. So that is another parameter which need to be fixed. So we need to fix the parameter data or the momentum parameter or memory parameter, momentum delta. And then we also need to fix the learning rate. Which we are going to relabel as a gamma here. That means that when we have done that, we would initialize with beta. So we have an initial value. So initialize a parameter I'm going to call V of I, which is the value for the first iteration for this additional term we get, V of I. And then what we are going to do then is, while stopping criterion not met, criterion not met, then we are going to update this V of I. Sorry, this should be V of I, since we are writing this as an iteration, V of I equal to this parameter delta multiplied with B of I minus the information from the previous step minus gamma multiplied with the gradient of beta of I. And then we update beta of I plus 1 equal to this beta of I plus this parameter V of I here. And this is end while. So this will be a gradient descent with momentum. So we need to fix the initial guess for beta 0. We fix the momentum variable, delta, and then we fix the learning rate. And then we initialize this variable V of I with a random value. So B of I, in this case, when you start with I equal to 0, you would often just set this B of I minus 1 to 0 in order to start the algorithm. And then you keep updating. So let's now look at the practical implementation. And this is going to be the last example today. So let's take a quick look at that one. Now we go back to the Jupyter notebook. And if you scroll down, there are several examples. You will also find the example of the previous case with ridge regression. So this is also useful for the project, because then you see for the case of a straight line, you have a pretty simple expression for gradients, etc. And then the Hessian matrix is also pretty simple in that case. You just get a diagonal matrix multiplied with parameters lambda, which also tells you that this is positive definite. But now let's look at an example here. So I have a simple function, x squared, which means that, and I hope you don't get offended by the simple cases. So the derivative is obviously 2 times x. And now I'm simply implementing gradient descent here. So I'm calculating the gradient, as you can see here. And then I take a step, the parameter beta, which we want, is simply going to be equal, in this specific case, it's going to be 1. Because we just have a function which is pretty simple, x squared. So then the solution minus step size times the gradient. So you can see I have now initialized my step size, which I set up when I'm calculating my function here. I do third iteration, I have a step size of 0.1. And then this function here actually plots my results. And what you see now, as a function of number of iterations, this is the gradient. Ideally, this should be 0. But you see, I take something like almost 28, 30 steps before my gradient is 0. And then you can look at the plot here and you see what is going on. So this is actually a nice way of visualizing. If I were to increase the step size, this could actually not converge. Now, if I then include momentum, which is something which often allows to get a better speed up in the iteration, especially if we have small gradient values. So if I add momentum, which is the next code, and this is something which we always end up adding because it gives normally a better result. So in this specific case, I calculate the gradient first, it's the same function. Now I calculate this term V, which I called, which is the step size times the gradient, plus this momentum times this change parameter. And then my new result is actually the solution minus this new change. And that goes back to that equation we had previously. And then you see now I'm putting this parameter to equal 0.3. So this becomes a hyperparameter, which people end up tuning as well. If I do that, if I run this code, what you will see now is that roughly after 13, 14 iterations, my gradient is close to 0. So this is a function which depends only on one variable. And then you can see now when we plot it, that we actually need much, much less steps before we reach that one. It's actually half of the number of steps. So this kind of gradient descent with momentum is something which we almost add by default. Now, the methods which we are going to look at now, like ADA-grad, root mean square propagation, and ADAM, and this will be next week. These are methods which are improvements of gradient descent with momentum. And they normally give much more stable results, especially when we have multi-valued functions. But I hope you can see all the kind of problems which we end up with when we are dealing with these type of optimizations. And I invite you to take just a quick look as well to the discussion which you have here. So the gradient descent is able to find minima, but it's very sensitive to initial conditions. Gradients become computationally expensive for large data sets, and these are problems which we will deal with next week. It's very sensitive to the choice of learning rates. And what it also does is that since we have a constant learning rate, all the gradients, so if you have 1,000 gradients you want to evaluate, they are multiplied by the same constant. So that means that the treats all direction in parameter space as the same or uniformly. And that may not be optimal. If you have one parameter which varies a lot and one parameter which barely varies, then this kind of brute force approach is not optimal. And next week, if we just summarize this week by these criticisms of standard gradient descent, which we can improve with momentum, then you will see that there are tons of things which we can add. So next week, we will discuss stochastic gradient descent, root mean square propagation, ADA-grad, and ADAM. And then we're also going to link this with automatic differentiation. So the material in the slides this week, I hope you don't get intimidated by all the material which is there, is something which we will continue with discussing next week as well. So this was just to give you the kind of overview of the landscape and all the problems we're going to meet when we deal with machine learning. Okay, I'm going to stop the recording here.